Good afternoon, everyone. My name is Aziz, as Abhilash said. So my first name is actually Ahmed, but since I think 90% of the population in Egypt are called Ahmed, so I have to go by Aziz. So today is just going to be a very crash introduction, a very basic introduction to what machine learning and data analytics are. There won't be a lot of like complicated stuff. I'd rather keep it like very simple to give first about an introduction about what machine learning and data analytics are, and like clear up the confusion from some of the buzzwords that we always hear about it. Okay, so as I said before I proceed, I would like to emphasize that this is a crash introduction. This is a very huge topic that lies at the intersection of several areas, including statistics, computer science, optimization, and other areas. And today we're gonna only scratch the surface and hopefully open up the eyes for what are the different applications that machine learning and data analytics are being involved at, and what is the basic underlying theory. And definitely there is a lot to know and discover that's still out there for you guys to explore, and for me as well. So this talk this tutorial, as Abhilash said, it's going to be very informal. If you guys have any questions, please stop me and just let me know. So this talk is basically a merger of multiple sources of information, mainly three of them that I would like to list over here. The first one is a very famous textbook called Elements of Statistical Learning by Friedman, Tibshirani, and Hastie. It's a very famous textbook that is written by great statisticians that covers a lot of theoretical aspects of statistics as well as implementations and examples. So this is something that if you guys are interested, you would definitely love to explore. The second thing is an advanced class that is being offered here in our department, which is ISIN 619. The title of the course is Analysis and Prediction, and it happened to be offered by my advisor, Professor Yu Ding, who got me introduced to these kind of concepts. So if you guys are interested as well, you definitely would consider taking such class. And lastly, there is a introductory to intermediate level course online, but offered by Coursera, which is called Machine Learning. It's a very popular online module, and it's taught by Andrew Ng, who is a very famous computer scientist, professor in Stanford, co-founder of Coursera, and a chief scientist in Google, so he's pretty knowledgeable in that area. And this course is actually one of the things that got me introduced to machine learning and data analytics. Okay, so let's kind of start. Where did it all start? So data analytics have been there since a long time, but it actually formally started to crystallize during the 20th century when the scientists started to propose theoretic framework to kind of observe physical processes that already existed a long time ago. There's a very famous example of a success story in data analytics during the 20th century. Where in the early 40s, the United States was doing all what it can to stop the Nazi invasion across Europe. And one good thing that the United States was doing is basically to invest in science for military purposes. It believed in scientists like Abraham Wald, who was a great statistician at the time, who was asked to analyze a very complex data set in order to take a very important decision during a very critical time of war. That data set was basically the bullet locations, the distribution of the bullet locations across the aeroplanes that came back from their trips across Europe. And the goal was to basically decide which areas of the aeroplanes were going to add more shields or more armor to minimize the fatality rate of these airplanes and maximize their success to return back to the United States. So it took Abraham Wald some time to reflect upon the data and to realize that the distribution of the bullet locations on the aeroplanes is not a uniform distribution. And he had to come up with a very interesting conclusion that sounded counterintuitive at the time, which is to basically put more shields and armor on the areas where no bullets were observed. This was a counterintuitive kind of solution, and his reasoning was that the areas that had a lot of bullets on them were basically represent the aeroplanes that made it back successfully to the United States, while the aeroplanes or the locations where no bullets were observed basically represent the aeroplanes that did not make it back to the United States, which means these are the weakest points that we should put armor and shields on them. So the moral of the story is that, first of all, data analytics is not the end of the way. Data analytics, and of course machine learning as well, is a tool that has to be used by some smart people in order to come up with smart decisions. And while doing data analytics, there is a lot of modeling, there is a lot of underlying theory, there is a lot of science that has to be done that kind of are confusing to some extent, because sometimes they intersect a lot, sometimes they mean completely different things, sometimes they mean slightly different things. So data first. Let's put the notion of what data means. Data is basically just a collection of bits and digits. So we have to always put that in mind when thinking about data. Data is nothing but a collection of numbers, bits, and digits that without data analytics, they don't make sense. And data analytics is the process or the set of procedures that and the set of actions that we do on the raw data to come up with insights and information. And this set of data analytics or this set of actions include anything you can imagine that can be done to transform these raw data to insights, understandings, and information. And this could include starting from cleaning the data, to processing the data, labeling the data, to further modeling using the data, learning from the data, and maybe predicting using the data. All this lie under the big umbrella of data analytics. And then there is another buzzword which is called data science that we always hear a lot, which means slightly different thing than data analytics. So as we said, as data analytics is the set of actions that are being implemented on the data, data science is the science that governs these actions. So this means slightly different thing in the sense that data analytics is the set of actions, data science is basically the underlying theory that tells you what to do when you implement data analytics. And a lot of people use data science interchangeably with what is called as the classical statistics. And while this is to some extent true because data science share a lot of aspects with what statistics is, however, it's slightly inaccurate because data science is a field that emerged from statistics. So it started as statistics, and then it kind of started merging with a lot of theoretical aspects and a lot of practical considerations from computer science to form up a new independent field that the people specialized in that field we would call as data scientists. So this is the difference between what data science and statistics are. It's basically a field that emerged from statistics, inherited the theoretical properties of statistics, and then merged with some theoretical and practical considerations of computer science. What is big data? So we always hear about big data as well. So while data analytics, as we said, is a set of actions, data science is the science that governs these actions. Big data is neither an action nor a science, it's a description. It's a description of what data that we observe nowadays are. So nowadays in many engineering systems, with the sensing technologies being advancing all the time, we have very large amounts of data. And it's not only about the volume. Usually you characterize big data as by something called the 5 V's of big data. And these 5 V's are the volume, the amount that these data sets are. They are so big that you cannot just traditionally treat them with traditional and classical database management techniques. You have velocity because the rate at which these data sets are being generated is very quick. You have variety because, and this talks about the versatility of the things that you're measuring. It's not only one input and one output. You have a lot of variables that are being measured, and these variables have different physical units, different physical meanings, and sometimes they could be qualitative variables, could be quantitative variables, and so on. You have variability because there is the data sets that are being generated, they are so big in number that you cannot represent them by just a linear function, for example. They are very complex. And then you have value as well because these value are kind of hidden as hidden gems in these big data sets that you have to extract. And this kind of analogy is what make people come up with the buzzword also data mining, which I did not list here, because you're basically mining for the value that is hidden within these big data sets. And then we have the word machine learning. And I'm sure there is a lot of confusion between machine learning and data analytics. They are used interchangeably sometimes. And as well, they intersect in a lot of aspects with the only exception that machine learning kind of evolved in a different environment. So while data analytics, as I said, emerged from the statistics literature, simultaneously the machine learning literature or the machine learning field was emerging from the computer science literature. And they both met somewhere to make the data science something feasible. So machine learning simply means that you have a machine, probably a computer, and you're trying to make that machine learn from the historical data. So it's like you're teaching someone to do some actions and take the decisions for you, or give you insights about something that you're trying to observe. So machine learning can be, in some sense, interchangeably used with data analytics. And finally, you have a buzzword, which is predictive analytics. Predictive analytics is a subset of data analytics or a subset of machine learning, where your main goal is to use the historical data to predict what's coming next. So it's not about like making insights. It's not about like extracting some sort of understanding. All what you care about in predictive analytics is making a prediction in the future. So these are different buzzwords. As you can see, they intersect a lot. But it's important to kind of make the distinction between each one of them. So, yes, sure.
Question on your description of big data and the 5Vs. I've heard of volume, velocity, variety, and value. I've not heard of variability. Can you explain again the difference between variety and variability?
Yes, sure. Okay, so very good question. These two technical terms are actually kind of very closely related. However, they kind of mean this different things in the sense that variety means that every variable that you're measuring has a very completely physical meaning than the other variable that you're measuring. So in a system, for example, you could be measuring the pressure, you could be measuring the temperature, you could be measuring, and these variables, first of all, they mean different things. And the second thing, they have different physical units, of course, and different scales. And the third thing is that sometimes they are even different in the sense that one variable is a quantitative variable while the other is a qualitative variable. So there is a lot of differences and there's a lot of variety in the variables that we're measuring. Variability is basically, you can have a univariate kind of data set that has a lot of variability. It means it's kind of a different thing. Variability is basically that the variance in your data is so big, and this variance is not just the variance at each like kind of observation. It's also the variance could be across time, in the sense that patterns and trends change completely over from time to time. So very simple algorithms sometimes, or most of the time, actually fail to characterize that kind of variability. I hope I clarified this. Okay, so very basic key concepts. Usually in machine learning or in data analytics, we have the notion of an output and an input. So an output is basically a response. Sometimes, of course, we have a scenario where we have multivariate outputs, but we're gonna first make the notion clear is that we have an output. This output can be referred to as many different things, sometimes called response, sometimes called independent variables, and it's often denoted by y. And this, as I said, can be quantitative, like the wind speed, for example, at certain location, and could be a qualitative, like in many medical experiments we would have, for example, the output as a yes or no, disease or no disease. There's no middle ground, it's either a 0 or 1. And then we have a set of features. So the notion features is widely used in machine learning, and it just means the input variables. So these are a set of variables that are thought to best describe the response, and usually referred to as x. For example, in the case of where the y is the wind speed, you have the different wind conditions, maybe that best describe what the wind speed will be, the medical measurements for the case where the y is a disease or no disease. And then you have the notion of a training data set, or a historical data in general. Training data set is just a collection of data where every observation in that data, you have a combination of the set of inputs measured at different values, and then you have an associated response. Repeat that for n observations, you have a data set of n observations. So this is the training data set. And the goal of machine learning in general is to use that training data to actually construct a functional relationship between the inputs x and the response y. So this is the general goal of machine learning. And when you construct that functional relationship, you might gain, or you might have different aims while doing so. Maybe your aim is just to gain insights about how x describe y. Maybe kind of project some understanding to the underlying physical process that you're trying to represent. Maybe your goal is to predict the outcome at different combinations of x. So you have n observations, but you want to establish that functional relationship that whatever value for the x, you're going to predict what the value of the y will be. And if the prediction is versus time, we refer to it as a forecast. So kind of the forecasting problem is kind of a problem that is a subset of the problems, general problems that we encounter in machine learning, where we're trying to build a functional relationship that could give us predictions. Some notations that we're gonna encounter during the presentation: the uppercase x is a random variable, the lowercase x is a value or a realization of that random variable, and then we have the x, boldface x here would be the vector or the matrix. We're not gonna present a lot of math, but just in the case for the few equations that I have, it's important to make the distinctions between these. Sure.
So when you're constructing this type of algorithm, and you have your data, you have your different inputs, what is it that leads you to picking a model that's maybe more predictive, or picking a model that's maybe more easier to understand, for instance? So what kind of leads you down that path?
Okay, so that's a very good question as well, because as you can see here, there are different kind of goals for machine learning, and depends on your goal, this will guide the selection of your model, right? Usually, I would say that the more common use of machine learning is to predict. Usually, this is what is known of machine learning, that you're trying to predict. That's right. So in industry, at least, maybe in research, there is a lot of emphasis on selecting a model that has physical representations. But in a lot of industrial practice, like for example, when we do research for wind kind of speeds and power, we keep representing all kind of physical interpretations of the model, but then it boils down at the end to that fancy table that you represent, where you beat the other kind of existing models in terms of predictive performance, whether in terms of root mean squared error, or whether in terms of, for example, of mean absolute deviation. So I would say that prediction is usually the most important goal in most applications, but definitely different goals could guide different model selections. Okay, so these are very, very basic examples that I'm just representing to make sure that the notations are clear, the notions are clear. So this is a typical example of machine learning, where let's say, for example, you're a CEO of a restaurant and you're trying to decide which kind of city you're gonna expand to next. And then you have already different food trucks, and these different food trucks generate to you some data. And in these data, you have data of 30 cities, for example, for which you have the populations of the cities, the geographic locations of the cities, the food tendency in each of these cities, and then the associated profits. And one thing that you want to do is basically construct that functional relationship between your output y would be here the profit that you want to make. This is the response that you want to target. Your x is going to be the populations, the geographic location, etc. And then you have this training data set that you have collected. So this is a typical example of a regression problem. A regression, and we're going to clarify the notion of what regression means. But this is a typical example of machine learning, where you're trying to kind of build that unknown functional relationship. A slightly different example, which is very common in software companies, is basically classification of emails, whether they are spam or good. And then you have, let's say, for example, 4,000 something email messages, and based on the percentage of certain words in the text, you're going to decide whether this email is a spam or not a spam. So this is a typical machine learning problem as well, where your y over here is a spam or no spam. So you can notice that the response now is a qualitative factor, not anymore a quantitative factor like the previous example. And the x would be the percentages of certain words, like the monetary, for example, values, the dollar signs, the bank accounts. All of these, when they are aggregated or accumulated in one certain email, then there's a very high probability that this email would be classified as spam. And this is an example of a classification problem. And then the last example that I'm going to present here is basically, let's say you have the energy consumption of customers. So this is a data set where for every customer you have the energy consumption. And then you would like to group these customers into groups with similar consumption levels, into, for example, low consumption, medium consumption, high consumption, and so on, so that you can, for example, decide on the price of electricity or anything. So here you'll notice that there is not really a notion of what is x and what is y. You only have one variable, which is the energy consumption. And in that sense, this is not like example 1 and not example 2. It's rather another application of machine learning, which is the clustering problem. So we'll now see in which of these subfields of machine learning do these examples lie. So first of all, we're going to make the distinction between supervised and unsupervised learning. So machine learning has two big branches. If you think about machine learning as the big subtopic, you have two big sub-branches, something called the supervised learning and something called the unsupervised learning. Supervised learning, you have a set of inputs and you have the response Y and you want to construct that relationship. So this is supervised learning. Unsupervised learning, the main exception is that only one variable or only inputs X are given and you do not have the notion of that notion of response. And this is a typical example of that is the clustering problem, where you have the energy consumption and you want to classify them into different classes. So supervised learning is a big subfield by its own and has a lot of literature associated with it. Unsupervised learning is the same. We're going to focus more in this talk on supervised learning, even though we acknowledge the existence of this unsupervised learning problem. Okay, so supervised learning itself can be categorized into two categories, two sub-branches. And these branches are regression and classification. In regression, the main difference is basically the nature of your response Y. If the response is continuous and real valued, then you would think that this is a regression problem. For example, the wind speed, the stock price, the wind power, maybe the profits in the restaurant example. In classification, your output Y is discrete, is categorical, and is qualitative. For example, disease or no disease, spam or no spam. There is no middle ground. And furthermore, there is a more general sense where you have the response that have multiple classes, not only like two binary classes, 0, 1. You may have like types of defects on a manufactured product. So it could be have class 1, class 2, class 3, but you still have the notion of response, which is Y being the defect types and X being, for example, the causes that lead to that response. Okay, so once we have the notion set up, let's talk about regression a little bit. Sure.
So I think I'm a little bit confused. So
Yes.
clustering seems like it could almost be classification, right? Because your outcome is you have maybe a multi-class grouping, or am I?
So that's kind of like your argument is very legit, but when you think about a clustering problem and think of it from the different perspective that you're trying to search for an X and Y, you wouldn't find any notions of X and Y in clustering. You only have the energy consumption, and that would be grouped into different levels.
Okay.
For the classification, you have some inputs, which, for example, let's say the defect types of a manufactured product could be, for example, in a, let's say you have the product, could be the size, for example, of, or for example, could be the manufacturing process parameters itself.
Right.
The manufacturing process parameters could be, for example, high laser versus a low laser, the cutting parameters, for example. So you have these inputs that either lead to a defect or no defect.
Okay.
Okay?
Got it. Thank you.
Sure. Okay, so regression. Now we clarified the notions of regression. So this is the basic regression formula. You have a Y, you have a set of inputs X, and you're going to assume that your Y is a function of your X plus some epsilon over there, which is called the random error term. And this random error term represents many things. It could represent any measurement error that could come from the observations. It could represent the model error itself. It could represent some noise in the process itself. But all what we care about here is basically this F. How we're gonna estimate this F so that it best describes the data we have at hand. And as I said over here, the essence of regression is how to choose your F appropriately so as to minimize the difference between the observations that we have at hand, which is Y, and F of X, which is the model that we decide to use for the data X. Okay? So this is a typical example of regression, for example. The green dots over there are some observations X, are some observations. We have the X on the Y-axis, the Y on the X-axis, and you can find that this function over there is a good representative function of the data. It accurately reconstructs the function between the inputs X and the Y in the sense that it kind of optimally passes through the data. This is the function that we are looking for. This is another example, but with two-dimensional inputs. We have the X, which is the years of education, the Y, which is seniority, and then your income is basically a function of these two, so these are the two inputs. And then you have the data, the observations over there, which are the red bullets, and what you're looking for is basically that hyperplane, which is decided based on your F function that would accurately and optimally reconstruct the relationship between the X's that you have and the Y that you have over there. Okay, so let's start with a very basic regression model, which is called the linear regression model. And the linear regression model is step one in machine learning. So this is, if you want to start learning machine learning, this is the first thing that you should understand. And in that model, we're going to assume that f has a linear form, meaning that we're looking for a line. So we're looking for a line that optimally passes through the data. So if we have something like that, for example, these x's, this x and y, we're looking for a line that would optimally pass through these data points. So how we're going to choose that line? So first of all, let's ask ourselves, how restrictive is that assumption? Well, it's a pretty restrictive assumption. That's why it's not currently widely used unless you have strong evidence of linearity between the x's and the y. Okay, but despite not being very widely used, it's kind of, once you understand the machinery and the system and the tools that are being used in linear regression, you can easily extend them to more complicated kind of regression models. And as I say over here, the word is non-linear. You're gonna rarely find that perfect linear relationship between the x's and y's. Okay, so the linear regression model assumes that your f of x is gonna be a linear function of your x's, and these betas over there are just the linear combination coefficients. So these take continuous values, and by plugging in any value for the inputs over there and substituting by the values of the beta, you're gonna get that line that best describes the data. So beta over here are the unknown regression parameters. So the problem reduces now, instead of arbitrarily saying which line are we gonna choose that optimally passes through the data, the problem now is more specific. Which values of the beta we're gonna choose so that to construct that line that is gonna pass through the data. So the problem reduces to choosing these beta values so that whenever I input any values for the x's, I'm gonna get an associated y. So ideally, we'd like to choose the values of beta, as I said, that minimize the difference between f of x, the line that we're constructing, and y, which are the observations. So given a set of data, this is where the machine learning part comes. We want to learn from the data how we're going to construct that line. So given a set of data, with the residual sum of squares, this is kind of a measure that is gonna define the goodness of that line. The residual sum of squares is just the deviation between the observations that we have, the y's that we have, and the f of x's that we're measuring. And you can see over here that RSS is a direct function of beta. So if we think of RSS as the deviation between the line and the observation, we're trying to make that residual sum of squares as small as possible. And the problem, as I said, reduces to finding the values of beta that would make this RSS as small as possible. So we want to minimize RSS with respect to beta. This is called, in the machine learning literature, which is a very well-known established problem, called the least squares estimation. You're basically trying to estimate the betas by minimizing the least squares over there. Okay? And it's widely used not only in linear regression, it's also widely used in a lot of different regression problems. So you can see that the goal is to seek the values of beta that minimize this function. And then there is a lot of simple algebra that is involved to come up with this nice closed form solution. So usually what you do is basically like the simple calculus courses tell us in order to find the value of beta that minimizes a certain function, you take the derivative and equate to 0. By doing so and doing the math, you'll find that beta hat is equal to this closed form solution. X over here is a matrix, and X is a matrix of where every row in that matrix is basically your combinations of the X's that you have in your training data. Okay, so the first row is the value of X1, X2, X3 realized at some certain observation. So we know X already from the data, and Y is just the vector of observations, the responses that you have already in your training data. So that you can see that given your training data, you can easily estimate the values of the beta that best minimizes the residual sum of squares. And this is an example where the data points are in red over there. This is the line that best minimizes the residual sum of squares using the estimated betas. And the vertical lines over there are just the sum of squares, the sum of squares. So the aggregate value of these sum of squares is basically the value, the measure that we're trying to minimize. And this is the same example, but in a two-dimensional setting. Okay? Any questions?
What is training data?
So the training data is just basically every observation in that data. This is given to you. This is we start with. Every observation in that training data, you have a combination of the x's and an associated y.
Okay.
Repeat that. You have n observations.
Okay.
Okay. Okay. So this is the linear regression model. Okay, there is a lot of nice statistical properties for that estimator. So here, this is an estimator for the true line that we don't observe. So there is a true line that best describes the data, and this is our estimator for that true line. So there's a lot of statistical properties, a lot of nice statistical properties that we're not gonna go through, but it's important to know that this is this tells us that this is an optimal estimator. Whatever value you're gonna plug for the beta, this is an optimal estimator. This is gonna beat any other estimator in terms of goodness, of that line. And they say, or like the theorem tells us, that these betas are called best linear unbiased estimators. So they are linear because obviously we're assuming linearity. They are unbiased because basically they're expected, if we think about it statistically, if we estimated multiple times using the data, you find that their expected value is basically, it goes to the true beta that best describes the data, and they have minimum variance compared to any other estimator that you would try. So just saying this is just a slide to tell you that this is a very nice statistical estimator. That's basically what it's telling you. And it has a lot of well-established statistical properties. Okay, so how do we do predictions now? We have that line that optimally passes through the data. How we're gonna do the prediction? We have the estimates for the beta. All what we're gonna do is basically plug in the values of the beta that we have estimated. Given a new point x, we're gonna substitute over there, and we're gonna get a prediction for the x star. Okay, so we already have the beta from the estimation. X is given to you as a test location that you're gonna, for example, predict for. You're gonna substitute and get the y, as you can see, as simple as it might sound. So this is an example in R. R is a statistical software language that is being used for such kind of models. I would highly recommend that if you have time, you would learn R. But kind of most of the stuff that R does, MATLAB also does. So it's kind of a matter of preference. But R is kind of very specific to only statistical problems, while MATLAB is kind of more generic and more general to other optimization statistical problems as well. So in R, for example, if we have these data points, I generated these data points using just this function multiple times, and I obtained these data points over there, these black crosses. And then it's as simple as writing that kind of line in R. Okay, so you don't really have to do the math. All you have to do is to basically write that line in R, where LM is just a function that does the linear regression for you. Y is the vector of observations. X is the matrix of inputs that you have. And basically this comes from your training data. And it will give you estimates for the betas. Okay, and here we have only one dimension. You have only one X, so we're only gonna get two parameters. The beta node, which is the intercept, as you can see over here, and the beta 1, which is the parameter associated with x1. And you can see that the beta node hat and the beta 1 are very close to the true values over there. So 10.32 versus 10, 1.96 versus 2. So it means that the estimator using the linear regression model is kind of it has some sort of optimality. And then how we're gonna do prediction, basically, as I said, just plug in this value with a new x star that you're gonna predict at. So this x star is 5.46 somewhere over here, and we're trying to get an associated y for that x star. So we're gonna plug in with the values of the beta that we have. You'll find that the y star that we predict is basically 20.99, which lies on that line over there, while the true value is the one in blue over here, which is 19.96. So you can see that our prediction is very accurate. But of course, and SE over here is basically the squared error. It's kind of y hat star minus y star squared. So you can see that the squared error is pretty small. But we have to say that the squared error is small because of a reason. And the prediction from the linear model does a good job because of a reason. Because you can easily observe that the data over here follows a very obvious linear trend. And this is not always the case in real case situations as well. So as you can see over here, this is a nonlinear data. This is a nonlinear process. We have x and y is a nonlinear function of x. If you try to fit a linear model to nonlinear data, you'll end up with this linear model that does not look as nice as this model over here. It kind of does not really capture the curvature that you can observe in the data. And when you try to do the prediction using the linear model for nonlinear data, you will end up having a prediction that is very different than what reality is. And you'll find that your squared error is now almost 1 order of magnitude higher than what was in the case where the data really followed the linear trend. So what we want to say is that linear regression model is a very nice model as long as the data itself is linear. But the machinery that we observed over here, most of them are extendable to a lot of other regression problems. So it turns out that linear regression is actually kind of a subset of a wider variety of models called polynomial regression. Okay, so polynomial regression is basically your f, instead of having a linear form, is going to have this parametric form where betas are now linear in terms of h of x's, not in terms of x's. Where h over here is some sort of a transformation that you decide based on your observation of the data. So if you decide h, for example, if you decide h of x to be equal to x, you will end up with the traditional linear regression model, right? Just substitute h of x by x, you will have the linear regression model. Choose h of x as equal to x squared, you get a quadratic regression model. Choose h of x as x cubed, you get a cubic regression model, and so forth. And as I said, it turns out that the same machinery can be directly extendable to the polynomial regression case using the least square estimation, minimizing the residual sum of squares. You exactly do the exact same procedure, and you find that by doing a polynomial regression, so this is the code in R that we do it with. You find that the curve now, or the fitted curve right now in green, is basically a very accurate descriptor of what the data looks like, and your squared error reduces to 0.94, which is quite small. Okay. So now we're kind of understood, at least from the big picture, what regression is, right? And what is the most basic model that is being used in regression, which is the linear regression model, and its generalization, which is the polynomial regression. Of course, there are a lot of more advanced models that are being used currently in research, but we're going to go through a little bit of them at the end of the lecture, because we said that the main motive of this lecture is basically to kind of highlight what the main keywords and buzzwords are. So classification. Classification, as I said, is basically, yes, sure, sorry.
Sorry, I have a doubt in the previous section. In the theorem, you mentioned that the errors are uncorrelated. What will happen if they are correlated?
Okay, so that's a very good question. If the errors are correlated, so you can still do the exact same procedure. You still can do the exact same procedure, but all what you're gonna miss is basically these nice statistical properties over there. Okay, so this is one thing. These nice statistical properties will not be achieved. And the second thing, because the errors are being correlated, maybe you'll end up with a poor predictive performance. And why is that? Because we're gonna show at the end of the lecture one of the kind of more advanced statistical models that I'm gonna show. It's basically assumes that the errors are correlated. Because in real life, sometimes the errors are correlated. I'll give you an example. Time series. If you observe something over time, like the wind speed, you would definitely have the intuition that wind speeds at time t is going to be similar to the wind speeds at time t plus 1, right? So there is this correlation between the wind speeds from different times. Also, you can have the notion of spatial correlation in the sense that the wind speeds at one location will definitely be similar to the wind speeds to the location next to it, but will not be as similar to the wind speeds to a location farther away. So you can see this correlation being inherent in the physical process that we're measuring. In that sense, your assumptions for the model will not be valid. You will still be able to do the same kind of machinery and the same kind of model implementation, but you might end up with poor prediction performance because you're violating what your actual physical process is. Okay. So classification. Classification is basically, as I said, when our responses are categorical. For example, this is, for instance, an example where we have X is your grade in mathematics and Y is whether you're admitted to grad school or not. So it's either a 0 or 1. And you can see that there is a very high chance when you have a grade of 2/10 in your math test, you're probably not going to be admitted to grad school. But at the same time, there are some unlucky people who scored near 8, but they ended up not being admitted. So the process kind of has variation, but at the end we're seeing that y is either a 0 or 1. So this is definitely a different problem than what we were observing in the past. If we try to force a linear regression model to a classification problem, this is what we get. A linear model over there. By just plugging in the data that we have to a linear regression model in R, you will have something like that. So if you want to predict, for example, someone who scored 5.7 in their math test, how they're gonna be admitted to school or not, you're gonna find that he's got a y of around 0.5, which doesn't mean anything, right? It's neither a 0 nor a 1. So obviously, the regression models cannot be directly extended to the classification problems. We need to introduce more concepts in order to establish the notion of that qualitative factor. So one possible solution is to instead of modeling y, would model the probability distribution of y, right? So the probability distribution of y, let's say the probability of y being 1, let's say we're going to assume that the probability itself is modeled as a linear function, okay? So we would think that this is a valid regression model. So in the sense that we have turned the classification problem into a regression problem. But then there is a problem, because the left-hand side is the probability, varies from 0 to 1, while the right-hand side can take any value on the real line, right? If you plug in any value of the x, you might end up getting a value that is greater than 1, or you might end up getting a value that is negative. So this model also physically doesn't have any meaning. So what do people came up with? They came up with this kind of quantity, which is called the logit function. So the logit function is the logarithm of the ratio between the probability of y is equal to 1 versus the probability that y is equal to 0. And what is nice about this form is that this logarithm of the ratio over there can take any value on the real line, and this right-hand side can take any value on the real line, so it's kind of physically makes sense, but at the same time it preserves the idea or the notion of probability, that this probability is limited between 0 and 1, this probability is limited between 0 and 1 as well. And this over there is called the logistic regression model, which is kind of a variant or an extension of the linear model in the classification problem. So the logistic regression model is definitely one of the basics models of machine learning, but it's definitely widely used in medical applications. So if you talk to anyone doing research in public health or in medical applications, there is a very wide reliance on logistic model as the basic model that they do for different medical tests that they do. Okay, so this is the logistic regression model. How we're going to estimate the betas. So now, again, we have these betas, which represent our function. By multiplying by x, of course, represents our function. And we want to estimate beta so as to best characterize the data that we have. And again, this is the essence of machine learning. We have some training data, and we're going to estimate these betas to best describe the data. So unfortunately, we don't have that closed form expression like this that was just a closed form expression of x's and y's anymore. Things got a little bit more complicated by introducing this logit function. So basically, we're going to write something called the likelihood function. And we're not going to jump or dig a lot into what a likelihood function is, but just to understand what it is, it's just a function that represents the agreement of the model that you're proposing with the data that you have, given a set of parameters, okay? So it's a function that measures the agreement. So just as the residual sum of squares measures the goodness of the linear regression, the likelihood will measure the goodness of the logistic regression by quantitatively measuring the agreement between the observed data that you have and the model that you're proposing given a set of parameters, okay? And in that sense, we want to maximize the likelihood. We don't want to minimize anymore. We want to maximize the likelihood, which is basically has this kind of form. And again, there's a lot of mathematics involved to come up with this form. So the likelihood function has this form. And what you want to do, again, is to maximize this function, or in other words, to find the values of beta that would maximize that function. And that maximization problem, by taking the derivative and equating to 0, is not solved in closed form, so we had to resort to something called the gradient descent method, which is basically a classical optimization technique where we want to optimize a function by iteratively trying different values, approaching gradually to the optimal solution, and so on. Okay, so this is the notion of what a gradient descent method is. So basically, by maximizing that function using the gradient descent methods, we end up with estimates for the betas that best describe the data that we have at hand. So this is the example, again, by doing logistic regression in R. You can see that now the model that we fitted in green is basically the logistic regression model. It gives values between, it gives qualitative values for the output, either a 0 or 1. Whatever input for the axis, you're going to predict either a 0 or a 1. So the outputs, as I said, here the outputs are logit functions or logit functions. So whenever you input an x, you're going to get a logit, and using that logit, you can have the probability of either being 1 or either being 0. Once you have the probabilities, which varies between 0 and 1, you can apply any kind of threshold. For example, if the probability is greater than 0.5, I'm going to assume that y is equal to 1, and so forth. Okay. Okay. Some practical considerations. So now we have clarified what regression, what classification is. Some practical considerations. There is something called the bias variance trade-off in machine learning. Again, I don't want to jump into too much details, but just to clarify the notions, bias is deviation from underlying truth, and we're going to see how each machine learning algorithm can be evaluated by its bias and variance. Variance is basically how predictive performance changes if you generate another data set from the same data generating mechanism. So what does that mean? Let's look at these two classifiers. These are two different classifications. We have two classes over here, the orange class and the blue class, and we want to find a classifier that best separates these two classes. Okay? So you can see that this classifier over here has a very simple form. It basically constructs a line, like logistic regression, for example. It basically constructs a line that best separates the blue class from the orange class. And you can see that the data looks like they are not perfectly separated by a line, right? There is a lot of orange dots that we are